Hi everyone. Today we are going to revisit the topics of law of sines and cosines. And once again, this is something that you covered in both geometry and algebra 1. So I'm going to move pretty quickly here just to kind of remind you how these things work. First of all, I do want to point out that these laws are designed to work with triangles that are not right triangles. So we learned SOHCAHTOA in the last lesson, and SOHCAHTOA is designed specifically for right triangles. These are adaptations of the sine and cosine trig ratios that can be used. Basically somebody proved a formula that uses sine and cosine that works on triangles that do not necessarily have right angles. Okay. Before we get started with writing down the formula for law of sines, I just want to remind you that when we talk about triangles, any triangles, we always name the angles with capital letters. And then we name the sides with lowercase letters, and they correspond according to the angle that they're opposite from. So if this is angle A, side A would be directly across from it. Angle B, so this would be side B, and then angle C, so this would be side C. This is going to be important when we write down our formulas that you know what we're talking about within a triangle. So law of sines is probably the easier formula to remember of the two. And it really just says that we can set up a proportion with sine of an angle over a side length and sine of another angle over its corresponding side length. And technically, we could set up all three in a ratio. We just only ever really need two at a time. Okay. And so your hope here is that, like, let's say, for example, we're using these two together. If you knew angle A and angle B and one of the two side lengths, you could fill in three of these values and then cross multiply to solve for the fourth. So let's try that in this first one. And I'm not going to pay too much attention to the letters or, whether I'm using A, B, or C here. I'm just going to make sure that I'm pairing things up that are across from each other. So the first thing I see here is a 44-degree angle that's across from the 7. So I'm going to set up sine of 44 over 7. And then I guess I should have started by marking which side it is I'm looking for. I'm looking for side AB, which is over here, and that's across from the 53-degree angle. So then I would say sine 53 over x. Now, if I had been looking for this side down here, I would have had to be using this angle up here, which would have been easy to do. I would have just subtracted these two from 180 to find that third angle. So just keep that in mind. Sometimes that's going to happen. Okay, I'm going to cross multiply here. So I'm going to go x times sine 44. Let's see, sorry, I'm going to write that in blue. You guys know how I am about my color coding. So x times sine 44 equals 7 times sine 53. And I'm not going to put anything into my calculator quite yet. I'm going to say if I'm solving for x here, I want to divide by sine 44. Divide by sine 44. And then this is the piece that's going into my calculator. The only thing you really have to look out for when you type this in is when you hit sine here, your calculator is going to open a set of parentheses. You need to make sure to close those parentheses before you divide by the second value there. So let's type this in together. You do want to make sure you're still in degrees. If you haven't changed it since the last lesson, it should still be fine. So 7 sine 53, close the parenthesis, divide by sine 44. And I end up with 8.05. And that looks reasonable in this triangle. Remember, the bigger the angle, the bigger the side will be. And so since this angle is larger than this one by just a little bit, I would expect this side to be a little bit larger than this one. So I think 8.05 looks reasonable. Okay, this next one makes us draw a picture, and there's something kind of unusual that happens with this one, but let's do the part we know first, and then we'll dive into some of the more complex stuff. So consider this triangle ABC, where AB is equal to 6. So I'm going to say this is AB with a side length of 6. AC is equal to 10. And then angle C is 33 degrees. tried to draw that sort of to scale. I don't know that that 33 degrees is super accurate, but oh well. And so we're trying to find the measure of angle B. So we're trying to find this angle right here. Okay, so if I was going to set this up like I did with the last one, I would immediately notice that the 33 is across from the 6. And so I can put those two together, and then the x and the 10 are across from each other. When we move on to law of cosines, people are going to ask, how do you know which one to use when? When do I use law of sines versus when do I use law of cosines? And this whole idea of having a side and an angle that pair up together, like I have here and here, that's how you know to use law of sines, is if you have an angle and a side where you know both values, I would always use law of sines. So I'm going to go sine of 33 over 6 equals sine of x over 10. And I'm going to cross multiply just like before. So I'm going to do 10 times sine 33 equals 6 times sine x. Okay. And then, whoops, now I want to divide by the 6 because I'm trying to get the x by itself. So divide by 6, divide by 6. And I'm going to type this calculation in. So 10 sine 33, close my parentheses, divide by 6, and I end up with 0.9077. That's kind of weird for an angle measure. Well, the problem is that's not really an angle measure, right? That is what's left over here. This is the sine of x. It's not x. Okay, we just solved for the sine of x. And so remember, anytime you have this situation where you're looking for the angle, you're going to end up having to use the inverse trig function. So now I'm going to do the inverse sine of that value. Okay, and it tells me that this is 65 degrees. Okay, so I should have known from the beginning, because I was looking for an angle measure, that at some point I was going to have to use inverse trig. And I think I mentioned that the other day, that anytime you're being asked to find an angle measure in whatever context, you're always going to end up using inverse trig at some point. Okay, so here's the weird thing with this question. And I think what I'm about to show you is going to make more sense once we do some more work with the unit circle this year. Okay, which don't worry, that is coming. But there's another possibility for this angle, and you may have learned about this a little bit back in geometry, but in this situation where I have an angle and two side lengths, this side is not really, because this angle can change, right? And so can the length of this side down here. So I want to show you what I mean. I'm going to use this to represent that length of 6 here, because that's fixed, okay? So that little spaghetti noodle there, that is a fixed length of 6, and we know that has to stay the same. But this angle at A can change, this angle down here can change, and the length of this side can change. So right now this side has to stay fixed going in the same direction because we have to maintain that 33 degrees. So it's not like this side can like swing out down here or anything like that. It's got to stay along this straight line. But remember, this line is infinite. This line could go on forever. Okay, so as long as this side length of 6 hits somewhere along that line, I can still make my triangle with the parameters I'm given. So watch what happens if I stick this down at point A and I swing this over this way and I have it come down and hit the triangle here instead. Now, that side length that I just put there still has a side length of 6, right? So I have this that's now a length of 6. I still have my 33 degree angle and my 10. And so now I'm looking at a triangle that looks more like this. Okay, where this is 6, and this is 33, and this is 10. And so obviously now if I'm looking for this angle, this is going to have a very different value than what it did before. Okay, we found that this angle was 65 degrees. This angle will not be 65 degrees. Okay, so I'm going to give you kind of the shorthand way to figure out what this angle could be, because I will tell you that in a question like this one, you would have to list both possibilities. And the question will probably say something like, give all possible answers, okay? The the way that you figure out what this angle would be is you take this 65 and you subtract from 180. Okay, and so that's what, 120, so 115. Okay, and if you look at the sine of 65, and that's awfully close to that 0.9077. Remember, we rounded the 65. If we wanted to stick with the whole decimal, we could have. And the sine of 115, they both come out the same. So when we did this step right here and said the sine of x equals this, and we asked our calculator, hey, what angle has this as a sine? Our calculator is going to give us one answer. There is always a second answer. And this is a topic that we are going to dive much deeper into in the next chapter, okay, why this happens. But what you need to know for right now is when you're doing law of sines and you're looking for an angle measure, you always have to consider this second possibility, okay? This is going to happen, or at least need to be considered every time you do law of sines looking for an angle measure, okay? Now, what is going to happen sometimes is you'll go ahead and do this calculation and you'll find an angle here that's so large that it can't possibly work, because when you put it together with this angle, it makes more than 180 degrees. And in that case, you just scrap that and stick with your original answer of 65, okay? But when you're looking for an angle measure, you always have to take that and subtract from 180 to find the other possibility, okay? Just in case this side decides to pick up and swing over this way. Okay. There's a couple different ways I could prove to you why this works, the 180 minus 65. So if you're curious about that, ask me in class and I'd be happy to show you. But I think that's something that once we dig deeper into the chapter 4 stuff with trigonometry will make a whole lot more sense. Okay. But for now, you'll want to make sure you have both of these answers written down on your paper. Okay. I think that's it for law of sines. Let's head over to law of cosines. Okay, the law of cosines looks like this. A squared equals b squared plus c squared. Notice those are all lowercase. Minus 2 times b times c times cosine of angle A. And my hint for you is in your triangles, whatever it is that you're looking for, whatever it is you're trying to find, label that A. Okay, so label the missing value, whether it be an angle or a side, whatever it is you're trying to find, as A or A, depending on whether it's a side length or an angle measure. And sometimes your triangles are going to have letters on it already. Like if you look at these two triangles here, they're already labeled A, B, and C. I would disregard those and re-letter it. Okay, I would make your own letters. So if I'm looking for side AB here, I can see that that's this side here. I want to call this side A then to fit with my formula. That doesn't really fit with how this is lettered, right? So I'm going to ignore these. Once I use that to figure out which side it is I'm trying to find, I'm going to say this is angle A, or sorry, this is side A, which makes this over here angle A. Those are the important ones to pin down. The other two side lengths are B and C, and it really doesn't matter which is which, okay? The A's are what's important here. Okay, so I'm looking for side A, so this is going to stay A squared equals B squared plus C squared, so 29 squared plus 13 squared, minus 2 times B times C times cosine of angle A, which is 41. So that's a little complicated, but the thing I like about it is this is all numbers, which means that can all go straight into the calculator. Okay, so 29 squared plus 13 squared minus 2 times 29 times 13 times cosine 41. And I get 440.95. Now you might be looking at the triangle and thinking that's awfully large, right? For this side length to be 440 if this is only 29. Keep in mind that what we just found is A squared. Okay, So now we have to remember to go in and take a square root on both sides. So I'm going to do the square root of this and the square root of this. Normally I'd be harping on you right now for remembering that you have to have a plus or minus answer, but the negative doesn't really make sense here because it's a side length. So I took the square root and I got this 20.998. I think I'm going to be comfortable calling that 21. So A is approximately equal to 21. And that makes sense with this triangle, I would say. Okay, looks reasonable. Okay, so now let's talk about the measure of angle A. So this one's already lettered the way I want it to be, right? Because if I'm looking for this angle, we want to call this angle A, right? Which makes this 10 your side A. That's going to be important. The other two are B and C, and it doesn't matter which is which, although because these are already labeled B and C, it would be nice to kind of keep those across from each other, but mathematically that won't make a difference. Okay, so this time filling into my formula, I know this value for A, the lowercase a. I know my side A is 10, so I'm going to put 10 squared equals, let's see, 17 squared plus 11 squared minus 2 times 17 times 11 times cosine of angle A. Now, don't get too far ahead of yourself here. Don't start typing things into a calculator. Notice that this time I've got a variable over here. So this is not going to be as easy as the last one where I can just put it all into the calculator. Also, I can't just put all of this up to here in a calculator. And let me show you why. I'm going to work through something off to the side. You don't have to write this down. But if I gave you an equation like 200 equals 5 plus 7 minus 3x, and I said solve that thing, you couldn't start by just doing 5 plus 7 minus 3. You couldn't combine all of those numbers because that 3 is attached to an x. You can't do this subtraction right here. You could do the 5 plus the 7, right? And then you could take that value and subtract it over here from the 200. But to get that 3 out of the way, you're going to have to use some division, right? So right here, there needs to be a separation in this equation. And that same thing happens here. All of this is attached to that cosine of A with multiplication. All of this is like that 3. And so right here where this subtraction happens, I have to stop myself from combining these numbers with these numbers because these are attached to cosine A. So I'm going to do this in pieces. I'm going to go ahead and do the 10 squared. I'm going to do the 17 squared plus 11 squared. And I'm going to go ahead and put these numbers together, these multiplication numbers. I just have to make sure not to combine these with these, okay? Because these are attached with multiplication to a variable. So let's see, 10 squared I know is 100. 17 squared plus 11 squared is 410 minus 2 times 17 times 11, 374, cosine A. Okay, the worst thing I see at this point is a lot of the times I see people remember that they have to do this in 3 pieces. Okay, so they do the 3 pieces, and then they get here, and then they go ahead and actually subtract these 2 numbers anyway. If I was going to subtract these 2 numbers, I would have just done it up here. I would have just put all of this together. The 374 is still attached to cosine A. So I can't combine that 374 with the 410. What I can do is move the 410 to the other side. So I'm going to subtract 410 minus 410. So I'll make sure I don't mess up my negative here. Okay, that's what I thought, negative 310. Didn't want my mental math to derail us here. Don't lose sight of the fact that this is a negative 374. And this is multiplication. Now to separate that negative 374, I'm going to divide. Okay, so 310 divided by 374 is 0.8289. And once again, that's kind of a weird answer until you remember that that's actually equal to the cosine of A. And once again, because I'm looking for an angle measurement, I'm going to have to do an inverse. So I'm going to do inverse cosine of this value. And I end up with 34 degrees. Okay, and that's it for this one. This is your answer. Now, is anyone sitting back and waiting to call me out on what we talked about on the other side when we were talking about law of sines? Remember when we did law of sines and we found an angle measure and we did this thing? I told you that when you do an equation like this, there's actually two different answers. Your calculator only gives you one of them, okay? And so I wasn't going to get into this on the other side, but now I feel like I have to explain this. Here's the reason that we have two answers. This is going to go back to the unit circle, which we will be revisiting soon enough. And so when I say, what was that value from the other side here? When I say the sine of 65 is 0.9077, a 65-degree angle is here-ish, okay? So this is 65 degrees. And the sine, if you remember, is the y-coordinate, okay? So the coordinates at this point are the cosine comma the sine, okay? And so that means that this value right here we know was 0.9077. Okay, if I go straight across the circle this way, I'll find another point that has almost the exact same coordinates, except the cosine will be negative this time. But notice your sine value is still going to be exactly the same. Okay, because these two have the same vertical distance from the axis, right? So these 2 points are going to have the same y value. And so this angle, whatever this is, starting from here going all the way to this line, is going to have the same sine because it's going to have the same y coordinate. Okay, and the way we figure out what that angle is we start down here at 180 and we subtract the 65 degrees that we would have moved over here. Because if this is 65 from here to here, then this is 65. So 180 minus 65 takes us to this point right here, which we said was 115. Okay? That same kind of thing happens with the cosine. So there would also be a point down here where the cosine value, which is the x, is exactly the same, but the sine value is negative. Okay? And so I could find that point by starting at 360 and backing up by 65 degrees. Okay? So if I wanted an angle that has the same cosine, I would do 360 minus 65, and that's going to get me to 295 degrees. So why don't I care about that one when I cared so much about this one? Well, if we're talking in a triangle, nothing down here is going to work inside of a triangle because all of these angles are bigger than 180 degrees. So when you're working with cosine, you don't have to worry about that second possibility. There is a second possibility there. And so if this diagram is confusing the crap out of you right now, I promise when we get deeper into chapter 4, you're going to understand it. We're going to spend a lot more time on this, okay? But what I want you to know is that when you're doing cosine, you never have to worry about there being a second possibility inside a triangle because the second possibility is always going to be bigger than 180 because you would find it by subtracting from 360. But the sine, there is a second possibility that could work in a triangle because it's less than 180 degrees. So when you're doing law of sines and looking for an angle, you have to look for a second possibility. When you're doing law of cosines and you're looking for an angle, you have to go through all this mess, but you at least don't have to worry about the second angle possibility. Okay, hopefully that didn't confuse the heck out of you. I promise all of that stuff about the second angle is a pretty minor thing. It doesn't come up a whole lot when you're doing these problems. Really, the core of today's lesson is the 4 examples. If you look at the math that we did in the 4 examples with law of sines and law of cosines, that's the most important thing to know for today. Okay, well, we will continue to talk about this in class after you try a few of these on the homework. If you're stuck, we'll make sure to go over them together. Good luck, and let me know if you have questions.